Today, I would like to talk about the Markov process and Fokker-Planck equation. The problem of determining the appropriate probability distributions of statistical dynamical systems not in equilibrium lacks a general solution, unlike the equilibrium case, in which a Gibbs measure, which is a maximum entropy distribution, is appropriate. A number of different approaches to this rather difficult issue have been attempted over the past century, but it is fair to say that none is entirely satisfactory. A very common approach is to divide dynamical variables into fast and slow. This can be assessed in various ways. For example, the ensemble mean of the variables could be calculated and the timescale of variations of this assessed. Alternatively, temporal decorrelation of the random variables could be calculated. One then assumes that the fast variables can be replaced with noise, which is a random variable with very rapid temporal decorrelation. White noise has instantaneous decorrelation and is the most commonly considered case. The objective then is to provide a model for the probability distribution for the slow variables of the system. A common assumption in this modeling process is that the probability distributions satisfy a so-called Markov assumption, in that the distribution at any one time determines future distributions. The associated random processes are commonly referred to as stochastic processes and have been extensively studied mathematically. Our focus will be on studying the time evolution of entropic functionals on such distributions in an effort to see whether there exists a second law of thermodynamics for such systems. We shall restrict our attention to the case that the slow random variables have outcome sets which are continuous. We shall also focus to begin with on the case where any realization of such variables is continuous in time, that it does not exhibit jumps in time. Stochastic processes in which the outcomes belong to the reals are immensely important in physics and other application fields. The most commonly studied such processes satisfy the Markov condition discussed earlier. A particularly important subclass of such processes is associated with the so-called Fokker-Planck equation. They are often referred to as solutions of stochastic differential equations. Crudely speaking, realizations of these processes are continuous but not differentiable in time. There exist other Markov processes in which a realization may jump discontinuously at a particular time. Examples of those are given by the so-called master equations. The Fokker-Planck equation is an evolution equation for probability density functions defined on an n-dimensional space of the form the partial derivative of the probability density function p of x and t with respect to t equals minus sum for I goes from 1 to n of partial derivatives with respect to xi of the vector ai times the probability density function plus 1/2 of sums for I and j go from 1 to n of double partial derivative with respect to xi and xj of the matrix Cij times the probability density function. We assume that the matrix Cij is non-negative, definite, and symmetric. The reason this equation is important physically is because it has the intuitive interpretation that realizations represent possible evolutions of a dynamical system which is stochastically forced by Gaussian white noise in time that is completely uncorrelated in the time dimension. The dynamical system has the form the partial derivative of xi with respect to t equals the vector ai depending of x and t. The Gaussian forcing has a covariance matrix given by Cij, hence the restriction on it mentioned previously that Cij is non-negative, definite, and symmetric. More rigorously, this equation is associated with the I-Stochastic differential equation, dxi equals the vector ai dt plus the matrix bij dwj, where wi are so-called random walk-Wiener processes. Cij equals bki bkj, and where we are assuming that repeated indices are summed. Three interesting results are available regarding the evolution of the ordinary and relative entropy within such a system. The first two apply to systems without stochastic forcing. Suppose we have a realization of a stochastic process obeying the Fokker-Planck equation with b equals 0. Then the ordinary differential entropy, which is a concept in information theory that began as an attempt by Shannon to extend the idea of entropy to continuous probability distributions, satisfies the evolution equation. The differential entropy, ht, equals the integral of the probability density function times nabla operator dot product vector a dx equals the mean of del dot product vector a with respect to the probability density function. To find out why this is so, I will show the proof. Let the realization of the process have probability density function f, then it follows that minus f logarithm of ft equals minus ft times logarithm of f plus 1. That is equal to del dot product vector a times f times logarithm of f plus 1. That equals f del dot product vector a times logarithm of f plus 1 plus vector a dot product del f times logarithm of f plus 1. This is equal to f del dot product vector a times logarithm of f plus 1 plus del dot product vector a times f times logarithm of f minus del dot product vector a times f times logarithm of f. And finally, this equals f del dot product vector a plus del dot product vector a times f times logarithm of f. Consider r equals minus f times logarithm of f as an entropy density whose integral over all space in the Shannon entropy. Corresponding to this density is a current J, which is identical to A times R, whose divergence may be seen on the right-hand side of the equation. For suitable restrictions on A and F required for the definition of Shannon entropy and for the Fokker-Planck equation to be well behaved, the surface integral of J is 0 for an infinite surface. The divergence theorem then ensures that the integral of the second term of the equation vanishes, and we are then left with an equation on the differential entropy. Notice that the importance of del operator dot product A to the entropy evolution, since A is the velocity vector of the dynamical system space, as I said before, that the partial derivative of x with respect to t equals the vector A, then del operator dot product A measures the time rate at which an infinitesimal volume element expands or contracts in the dynamical system. When it vanishes, the system is said to satisfy a Liouville condition. As we saw in an earlier lecture, systems of molecules obey Hamiltonian dynamics, in which this divergence vanishes, so entropy is conserved for such systems. The relative entropy, on the other hand, is conserved in all systems with b equals 0. Suppose we have two realizations of a stochastic process obeying Fokker-Planck equation, which have the additional condition that b of xt equals 0. Then the relative entropy of the two realizations is time invariant. To prove it, let the two realizations of the process have probability density functions f and g, then it follows that after many transformations, f times logarithm of f over gt equals minus nabla operator dot product a times f times logarithm of f over g. In this case, the entire right-hand side of the evolution equation is in the form of a divergence of a relative entropy, density, current, and as argued in the previous theorem, this implies that the global integral of the left-hand side vanishes by the divergence theorem. In many classical systems with B equals 0, if one calculates the relative entropy with respect to a particular finite partitioning of state space, rather in the limit of infinitesimal partitioning, then the conservation property no longer holds, and in nearly all interesting cases, it declines with time instead, and the system equilibrates. This reflects the fact that as time increases, the difference in the distributions tends to occur on the unresolved scales, which are not measured by the second relative entropy calculation. This coarse-graining effect is often related to the next result. Now we have the stochastically forced case. Suppose we have two distinct, or in other words, differing on a set of measure greater than 0, stochastic processes obeying Fokker-Planck equation with C equals B times transpose B. Positive definite almost everywhere, then the relative entropy strictly declines. As in the previous theorem, we consider the relative entropy density function R equals F times logarithm of F over G. The proof of this shows we need only consider the time rate of change in this function due to C, since that due to A leads to no change in time of the global integral of R. The change in R due to C may be calculated using equation Fokker-Planck equation. Here we have RCT equals logarithm of F over G plus 1 times the double partial derivative with respect to xi and xj of Cij times F minus F over G times the double partial derivative with respect to xi and xj of Cij times G. We are using the summation convention for repeated Latin indices. Now it can be seen that the double partial derivative with respect to xi and xj of Cij times u times w equals w times double partial derivative with respect to xi and xj of Cij times u plus 2 times partial derivative with respect to xj of Cij times u times partial derivative with respect to xi of w plus Cij times u times double partial derivative with respect to xi and xj of w. We are using the symmetry of C. Writing G equals F of G over F and applying the last relation, we derive that the second term of the given equation is like it is shown on the screen. By combining this with the first term, we get a cancellation of part of this equation with part of the first term of equation on change in R due to C, and so we obtain that the change in R due to C equals logarithm of F over G times double partial derivative of Cij F minus 2F over G times partial derivative of Cij F times partial derivative of F over F minus F over G times Cij times F times double partial derivative of G of over F. Now to this equation, we add and subtract given terms and use equation on double partial derivative we wrote earlier to deduce the new form of change in R due to C by using the definition of R as well as cancelling two terms involving the partial derivative of Cij times f. Finally, after many transformations, we obtain a change in R due to C equals double partial derivative with respect to xi and xj of Cij times R minus f times Cij times the partial derivative with respect to xi of logarithm of f over g times the partial derivative with respect to xj of logarithm of f over g. The first term on the right is of the form of a divergence, and so using similar arguments as previously does not contribute to the evolution of the global integral of Rc. Actually, the positive definite nature of C shows that it is purely diffusive of the relative entropy density R. The second term is negative almost everywhere due to the fact that C is positive definite almost everywhere, and that f and g differ on a set of measure greater than 0. Thus, in that situation, if we take the global integral of Rc, we conclude that the relative entropy declines strictly with time. The third theorem shows the central role of stochastic forcing in causing relative entropy to decline monotonically. This behavior is sometimes called a generalized second law of thermodynamics, and d of f and fec with fec the equilibrium density for the system has been proposed as a non-equilibrium entropy function, where it is referred to as the conditional entropy. Note also that this result holds for any two densities satisfying the Fokker-Planck equation, not just f and fec. This result was first proven in 1957 by Lebowitz. It is a crucial result in the theory of the Fokker-Planck equation, in that it allows a deduction of the convergence of a density to an equilibrium density as t tends to infinity. It is possible to extend the Fokker-Planck equation to include discontinuous jump processes, and then this equation becomes the more general Chapman-Kolmogorov equation. The additional terms are often termed to as the master equation. It is then possible by similar arguments to those given earlier to conclude that the jump processes result in an additional strict monotonic decline in relative entropy. There is also a very interesting connection between these results and the so-called kinetic theory of Boltzmann, which applies to dilute gases, which will be discussed next time. Thank you.